Hi, my name is Dan, and this video is one in quite a long series of videos in which I use this digital simulation software called Digital Works. I'm going from the basics of fundamental logic gates to creating a working programmable 4-bit CPU. We're quite late on in the stage now. We're putting the CPU together from the components that we've previously made. There's a roadmap of where we're going in the description down below. We're only a few videos from the end. And there's also a link to the software that I'm using, which is called Digital Works, which is free to use. I'm using a simulator because A, it means I don't have to buy any hardware, and B, it's actually more visual than doing a whole lot of soldering up pieces of hardware together. You can do it in the circuit diagrams and make it simulate, which is great. Anything else I need to say in my introduction? We're very specific now to the this particular CPU design, which I have created. All CPUs are different. A lot of the stuff that we've done in the videos, particularly early on, is very generally applicable. So stuff about registers and decoders and multiplexers and so on. But there are parts of this that are very specific, which are the ALU is quite specific, and the control unit is incredibly specific. And that's the thing that we're now going to introduce into our CPU, is our control unit, which we previously made. So let's go find it. If you're playing along with me, and I hope you are, then you've had a whole lot of stuff going on. And you've made all these components that are in the parts center. And it's been a long ride, but we're nearly there. Here's our control unit, and we're gonna link it up to the op, which is above. I'm just gonna tweak this so it's about as far to the right as I can make it for where our op register is, to give me as much space as possible for these controls here, which are all the controls that are coming out of the control unit. And if we get too tight when we're wiring it all up, we might need to ease it out a bit further and ease the op out. I'm kind of wondering if I want to just do that straight away. And let's. Is there any reason why not? And the answer is it just takes a little bit of work. So I'm not going to take it quite all the way up, because I'm aware that there are these things to come through this gap here. And I'm just going to take each of these in turn and slide them up. And slightly tidying it up as well at the same time. The spacing of these is not as good as it could be. And I don't want to be really fussy about this, but if I do that, it makes it look slightly better. Right, let's start wiring up. So let's make sure we wire up all the inputs first. And this is the op. So this is coming out hardwired out the op register. And you'll see that I haven't tidied up my control unit. It's still this really wonky thing with the words at an angle and stuff like that. But I decided that was a tidy up that I couldn't be bothered to do. Right, so we also want to wire up the fetch, execute, and the increment. We need the ring counter in. Will I do that first, or shall I do C and Z first, which come out of here? Let's put the ring counter, sorry, the ring sequencer in first. So I'm going to put that down at the bottom here. Am I going to sit it on top of things here? My vertical space is where I feel like I've got some limitations. Oh, sorry. So I'm just going to slide that up a little bit. And I'm going to sit this cheekily kind of over there. Is this a good idea? I'm not sure what is a good idea here. I'm going to move my program counter even further. That's the answer. And this means I need to move all these wires. So sorry about this, bear with me. This, of course, is a circuit diagram, not a physical layout of components. And the physical layout of components could be very different to the circuit diagram. But we're not going to make a physical layout of this, or I'm not. If you decide you want to, then that's entirely up to you. You're welcome to use my design to do that. And I'm just going to set this down a little bit, give some space there. So some of these need to go through there. The increment comes at the end. So as I described before, what I'm going to do in terms of these phases is I'm not going to wire around and make it a 6-bit, sorry, a 6-phase. I'm going to keep it as an 8-phase. And what I'm going to do is I'm going to ignore the first phase and the last phase. And that just gives it a little bit of gap between each cycle, which I found that when watching it, that just can help very slightly. So I'm going to wire up the second one to be fetch 1, and we'll wire in sequence from there. Fetch 1, fetch 2, execute 1, execute 2. Trying to line these up by eye. And then we're going to have ink 1 and ink 2. Again, I'm going to tweak the program counter again. I'm just going to move it upwards. Just so that, I mean, you know, theoretically, this space where the part center is all wasted space, apart from the fact that I want the part center there whilst I'm building. But I don't need it there all the time. And I've just done that so I can squeak these wires out there without just making them crazy. So ink 1 is going to there, and ink 2 is going to there. And it's tempting to stick a set of LEDs on there to help us keep track of what's going on. So I'm just going to cheekily interleave those between the wires and connect them up. I hope it's not too confusing. That's kind of on top of the wire. Is on top of the wire okay? Probably is. Depends on the wiring up. So I'm just going to connect these up like so. That is going on the wire. I've got to be careful about this. I'll delete that one. Back to wiring. So I can tell when it's actually attached to the LED because it goes white. There we go. Slightly fudgy that, but not too bad. Right. C and Z, which need to come out of here. I'm just going to, again, to make sure I give myself as much space as possible, I'm just going to bring them down and then round. I'm going to go round a bit round. Which one is this? This is C out, so this one's going to C. I was tempted to move this as far across there as possible. It's not going to be so much of a problem because um, we're okay in terms of space generally. The only things that's going to need to come in this direction now are control for the program counter. Um, keeping it fairly neat. Right, so the big job is all these stuff here. And they're not, I haven't put them in any great order. So let's do the output enables. And please bear with me if I feel the need to kind of tweak some of this. But the output enable for MDRO, which is the ops. So that's this one up here. And what we're going to try and do is start by doing these as with as few corners as possible. But as we move on, we're just going to end up with the need for more and more corners. So output enable for MDRD, which is this one. And I'm going to do this one backwards. I'm going to go through that annotation there. And line up next to this one so that I can go in there. Output enable for data. So this is data, that's the output enable. We're almost directly across. So let's actually take that across there and tweak it towards the end. Kind of make it absolutely straight, not quite. Well, straight, what I meant was horizontal. It all depends on the lining up of these pins. Output enable for the program counter. So that one is all the way under there. Okay. Which way around shall I go? Is there any reason not to go over the top? And my answer is no, there's always an excuse to go over the top. So none of these should need to have OR gates connected to them because the only thing that should be talking to bus reads and output enables is the control unit. It should be controlling all this access. Let's go A. Sometimes the design of CPUs is done so that instead of doing it quite like this, then you use a decoder for your output enables and possibly also for your bus reads. More likely for your output enables. And so what you do is you create a binary number to say which element can talk to the bus. This is kind of slightly more sophisticated bus control. And the reason for doing that is because you only ever want one thing that is output enabled to the bus at once. And if you use a binary number and then decode it, you have a reasonable confidence that that is going to be the case. However, we've just been careful, or I hope we've been careful in our control unit, and that we're never going to have this bus contention. Where am I going? I'm going across to B. This is not looking too bad so far. I know I'm way less than halfway through. ALUX, so that's this one down here, because that's on the ALU. So again, I'm going to bring that so it's fairly tight up against these lines, trying to make sure I keep enough space going on. Right, so that's the output enables. So memory read is the next thing. And so memory address register, sorry, not memory read, bus read. So we're going up there. Bus read. In fact, let's see if we can bring it down this way. So go past all these. You should be able to come. Yeah, have we got it lined up? It's close. Pretty good. Memory data register for data, so the bus read for this one is what we want. So that's there. Okay, I can feel us running out of space here. But never mind. So that across there and take it up close to that one. We've got space to squeak this through this gap. Yes. Up. So that's up here. Bus read. Again, we're a little confused around here already, so let's go up and over. The only issue with kind of doing up and over is that, so if you make your wires longer, it doesn't actually have any particular effect on the simulation. It just fills the space more and more. Not output enable. So I'm going to need to redo this. Delete this object. Up. There we go, bus read. Right, what we got next? Data. Bus read is there. If I tried to put it along there, it'd be too much along that line. So we're starting to get some craziness going on. I thought we would towards the end. Is it the end? I'm not sure. So let's do it like that. All the while I'm kind of trying to go around the edges of things to give myself more space. PC, program counter, bus read. And as before, we went over the top, so why not with this? There's still some space to come up through this gap here. And we're going to need to move the parts center, but that's okay. It's quite happily, we'll keep that wiring thing connected. We're coming down to bus read, so we can cross over there and come down. So that's program counter A and B. So A, bus read, starting to run out of space up the top. We probably can pull one through there. We might be able to get two, but it starts to get a bit tricky connecting up there. So let's save that top gap for B and let's bring A down the bottom. So I'm just going to, so I'm trying to line up so that I can go kind of through this gap here. Remind me what this is. This is a bus read. There we go. And same for B, and we saved this gap up the top specifically for this. Starting to get quite a lot of corners in these. Right. Halt. I'll deal with that when we do the controls, which is in a separate video. So we've got read O and read D. So read on the op memory is there. Just asking myself exactly how I'm going to line this up. I'm going to do that kind of thing and then bring it to there and then bring it down here for read O. About level. Perfect. Read D. So read D is here. I'm going to bring this kind of around the other side. I'm going to cross over those two, come across there, and then drop down here. D, right D. So similar, I'm just going to follow that other one around. I'm going to cross over it here. And I've got lots of things going through that annotation that says that it's the memory data, but never mind. Right D. Oh, nearly there. ALU execute. So that's this one here. And we are kind of running out of spaces here. So this is getting a little bit cornery, but never mind. And finally, ink. Now, ink goes from here into the program counter, and we've done traditionally going up and over the top for these, so we'll do that again. We've still got space. The good news is there's not a lot more to do in terms of wiring. These are slightly crazily ordered. Won't get them here, but never mind. Oh, ink, not clear. Right. Okay. Now, have we got everything connected? I guess the important thing for the program, the control unit, is not only is it connected, but is it connected to the right thing? Because that's going to be really important for us. So let's double check everything. We've got our ring sequencer, which is doing our 6 phases. The first one out of the 8 and the last one, we're not wiring up so that we've got this little gap between the 2 phases. We could have done it 0 to 6 rather than 1 to 7, but sorry, 1 to 0 to 5 rather than 1 to 6, but that's not important. And actually, interesting, one of the reasons for having this so that we don't use the first one is that the starting state, the kind of at rest state, has got this high. So it is actually useful to not have the fetch high to start off with, to actually just allow that to not be permanently on when we're stopped. Right, back to where we are. So fetch, I'm kind of going to use my pointer to follow. That's fetch 1. Second one, my eye's going to go cross-eyed trying to follow these. Is it easier if I just hold, click on the wire? That's fetch 1. Yes, it probably is. Fetch 2. Next one, X1, X2, ink 1, ink 2. Perfect. We've not plugged in go and reset yet. That's part of the controls, which we'll do in a later video. Right. We've got op 3 to 0, wide in. That's good. We've got C. Let's check that that's going round to C out. Okay. And Z is going to Z. I like this. Clicking on the wire. This is a good idea. So MDRD. These are output enables. Output enable from. No, it's MDRO. I found the O and the D a little bit difficult to see the difference, but it is O, this one, and that's correct. It's on the output enable for the memory mem op. So this should be output enable for mem data, and it is. This should be output enable for the data register, and it is. Look at that wire there; it's kind of crazy. And this should be output enable for the PC, and it's dotted. It is. Let's try A. So earlier, when we swapped, in the previous video with the ALU, when we swapped A and B around, and all we did is swap the annotation around, at that point it wasn't important which one was labelled which. What's important is how we wire it up to the control unit. And then, of course, how we wire it up to the ALU. So that's the A, output enable. This should be B, output enable. And it is. This should be ALUX, output enable. So that's the output enable from the ALU. Yes. Right, bus reads, memory address register, bus read, yes. Uh, memory data register for data, yes. Op register, bus read, yes. Data register, bus read, yes. PC, so that's the program counter, bus read, yes. A register, bus read, yes, let's just tidy that. B register, bus read, yes. Halt connected later. Read for the op memory, yes. Read for the data memory, yes. Write for the data memory, come on, yes. ALU execute, yes. And inc, which goes through to the program counter, yes. That appears to be our control unit wired up correctly. That now is the full CPU. And the things that we're going to add now are not conceptually part of the CPU as a CPU. I'm going to add some extra stuff over the next couple of videos in order to allow us to control this, and then in order to allow us to input data so that we can create programs that can be run. So let's have a very quick look at what we've got. This is a monumental point in this. The wiring there's lots of wiring. I knew this was going to be the case with the control unit, obviously, because there's lots of stuff coming out. Hopefully, you've kind of followed, well, more than kind of, you have followed everything that's going along, and you should therefore know what every single one of these wires does if you've been through the whole process with me. And just a quick recap of what we've got. We've got two buses. We've got this bus, which comes down here and actually now extends down along here. We've got, and maybe our program counter would have been better there, but who cares? We've got two memory banks. We've got the opcode memory bank. We've got the data memory bank. I'm just going to move that annotation down to there. This one is nicely upside down just because it made the wiring go better. And then we've got the op and data registers, which hold the information that's been pulled out of the memory for our program. Mostly this is going to be the op. The op is wired up to the control unit, which tells it how to route all sorts of things, and directly to the ALU, which is what this set of wires are. We've got general purpose A and B registers. Actually, they're not general purpose. They're linked directly into the ALU, which can do our maths for us. We've got the program counter, which keeps track of where we're going with the program. And we've got the ring sequencer, which actually gives us our sequence of things. We're going to save, and we're just going to hopefully see something going on if we say go. We won't have any data in here, but it'd be just interesting to see if something runs. But we'll save first, and then I'm going to simulate and use this to. We haven't even got anything wired up to it, so let's wire up a simple control to go. What we're actually going to want in our controls is more than this. We're going to want the ability for it to turn itself off when it gets to the end, for example, and a few other things. So this is going through. We can see the phases here. But actually, the data that we seem to have is ones. And the reason for that is because everything all our memory cells set themselves to 1 when we start as a kind of feature of the flip-flop that we've got, in fact, very way back at the SR latch. That was what we found. What we can see, though, is that this ring sequencer is going around, and the program counter is incrementing. So we should find it's gone up to 0101, and it will go all the way around, hopefully. And we've got lots of different wires that are being hit as well as we go through the different phases. You can see lots of things happening. But we want better control. So we'll implement that in the next video. That's it from me for now.